All right, so when we talk about trig functions, we had a section in our notes where we said that trig functions are going to be, and I'll just flash this up here really quickly, trig functions are going to be continuous on their domain, and you have to restrict it to its one-to-one for the inverse to exist, but you also have to think about vertical asymptotes for trig functions when you have anything besides sine and cosine. So tangent of 2x looks very innocent there. It looks like there's no problems whatsoever. But remember from our trig class that tangent of x is the same as sine over cosine. So this is really tangent of 2x is sine of 2x over cosine of 2x. And if you have a fraction, as we talked about in the last couple examples, that means you got a big issue as far as continuity goes. So when you rewrite this, you see that this function is going to be continuous provided that cosine of 2x is not equal to 0. Now, this is where we really have to go back to our understanding of trig. So we are trying to figure out here where cosine of 2x is equal to 0. Now, if this was just cosine of x, there would be no problem. Look on the unit circle has cosine x. But because this is 2x, that is what we call a multiple angle. It's not just x, it's 2x, and this becomes a multiple angle equation. And hopefully you remember from trig, when you have a multiple angle equation, one way of doing this is to let theta be equal to that multiple angle. So let theta be equal to 2x. Now, if I do that, I then have cosine, instead of this 2x, I have cosine of theta is equal to 0. Now, that I can solve because that theta is on my unit circle. So what I'm trying to do here is figure out where cosine, which is given as the x-coordinate, is equal to 0. Now, that is going to be at pi over 2, but it's not just at pi over 2, it's at any integer multiple plus that. So if I add pi to pi over 2, I would also have an x-coordinate of 0. If I add another pi, I would also have an x-coordinate of 0. So our solution here is going to be theta is equal to pi over 2 plus any integer multiple of pi. So we represent that with n pi, where n is equal to an integer. So we're talking 0, plus or minus 1, plus or minus 2, dot, dot, dot. Now, we were not interested in theta. We were interested in x. So the multiple angle equation is once you solve it, so you let x be equal, or 2x be equal to theta, you solve that equation, and then you go back to the fact that theta is equal to 2x and substitute in. So here my theta will be replaced with 2x equals pi over 2 plus n pi. And we're trying to solve for x. So to solve for x, I'm going to have to divide each of these terms by 2. Divide by 2, divide by 2. So that will give us x is equal to pi over 4 plus n pi over 2. All right, so those places at this point is kind of like, well, what was this all about? Remember that at the very beginning, it's continuous if cosine of 2x is not equal to 0. We solve for x, we get this value. We do not want this value. Those are where we have the discontinuities. So we can say that this function is continuous provided that x is not equal to pi over 4 plus n pi over 2. Now, when you get to this answer, you then have to identify what type of discontinuity. So there will be a discontinuity at pi over 4 plus n pi over 2, where n is an integer. And because you're dealing with a fraction, you have to ask yourself, can you remove that denominator? And if you look back up here, you guys, at sine 2x over cosine of 2x, there is no way that that cosine of 2x is going to somehow cross out with sine of 2x. So this is non-removable. The denominator is not going to cancel. And because it is not going to cancel out, we say it's non-removable or that we have an infinite discontinuity there. So we would have to say, and I know this is a lot of flipping around here, but going back to the bottom of this page here, we would say that this discontinuity is an infinite discontinuity that happens at pi over 4 plus n pi over 2, where n is any integer.